Okay, we are back on track with the schedule. So now I would like to introduce Phil Trinder, who will be talking about a new profiler for Haskell on Numa systems. Interesting stuff. So, Phil, the stage is yours.
Thank you very much, and welcome all. Thank you for giving up your Sunday. I guess the good thing is this is the start of ICFP. People aren't yet worn out, so you'll have lots of energy to listen to the talks. And it's going to be a bit tough to follow the last talk, but I'll do my best. So this is work primarily done by Rory McGregor, but also, well, supervised by Hans Wolfgang Leudel and I. Hans Wolfgang's based at Heriot-Watt. Oh, now. Perfect. Okay, so this is about looking at how GHC Haskell works on non-uniform memory access architectures, or Numa architectures. Numa architectures partition the RAM into regions. Each core is associated with a region. It can access any address in the memory, but access to the local region is around twice as fast, and the bandwidth is about twice as great than it is to some remote region. And these are becoming common already. The servers that are running, likes of Facebook and Google, they're running on Numa boxes. And as the number of cores is increasing in general purpose machines, so AMD Ryzen chips in laptops have a Numa architecture. So more and more machines use Numa. So this talk is about profiling Numa. You can understand what a program is doing on a Numa architecture at a number of different levels in the system stack. So you can understand it at the hardware level. There are the modern chips provide counters that record things like how many accesses are to the local region and how many are to a remote region. You can also look at things, so the low-level counters are very detailed and finicky to deal with. There are tools at the operating system level, things like Numactal, and we're going to use a NumaProf tool at that level. Potentially, a language implementation, a virtual machine or runtime system can keep track of where memory accesses are being targeted. And in some languages, like C or C++, you can actually allocate memory into a specific region. But of course, most languages don't use explicit memory management. In fact, no functional language does. But the languages with automatic memory management, like Python, Java, they are the most widely used languages that are running all these clusters and cloud instances. Now, these languages don't have any Numa control of the memory. The opportunity associated with that is the implementations both know what the program is likely to do, it has more information about what the program is going to do, but also it can freely move objects in memory without changing the semantics of the program. So you can hope to optimize the program without changing its semantics. And we don't think there are huge wins here in terms of execution time, maybe only 5% on languages like Java or possibly Scala, but a 5% in the number of JVMs that run globally is a huge amount of carbon and energy. So this study is about Haskell, not about Java or Python, but we think Haskell is a really interesting language. It's kind of an edge case language because it has it places such high demand on the memory system. It has massive allocation, deallocation rates, gigabytes a second. Why is that? Well, state is immutable. If you update a data structure, you replicate at least part of the data structure. So you're forever creating new objects. Likewise, lazy evaluation means that closures are being continually constructed and destructed as the evaluation proceeds. And this drives this massive allocation and deallocation rate. So in some sense, understanding how Haskell works on Numa is understanding an edge case, the limit case for language implementations. Ooh, I've frozen. Okay, so I need to tell you something about memory management in parallel Haskell. The GHC parallel Haskell. The GHC runtime system uses generational garbage collection. So this is based on the observation that objects die young, and you allocate into the first generation, and you hope to have garbage collected many of the items in the first generation before you fill it. And when you do so, you copy the more long-lived objects into the second generation. The runtime system maintains a separate area for static objects that are generated by constant expressions, so-called CAFs, constant applicative forms. And the runtime system has something called a Haskell execution context, or HEC, for each core. This is where sparked threads of execution that are created by a par construct, where they execute. And since GHC 8.2, those sparked threads explicitly allocate into the hex Numa region. So each hex is in a region, and all allocation is done local to that region. However, the main thread, which is where the program execution starts, Haskell has a main function, and that's where the execution starts. The main thread is unpinned. It may run in any Numa region. So what I'm going to do is I'm going to report a fairly systematic study of some GHC Haskell programs running on a specific Numa machine. The machine is called Togian. It's a typical Numa server. It's got 64 cores and 8 regions. And the access latency from each region to each other region is as follows. So the diagonal access latency, these are relative access latencies. Diagonal means access to your local region is fast. It's given a nominal 10, value of 10. Access to remote regions may either be 60% slower or 120% slower. So increased by to 16 or to 22. And you'll see the relevance of that shortly. Okay, so the benchmarks we've studied are 8 benchmarks from the NoFib suite. There's a table in the paper that reports results for all of those programs, but to make this talk comprehensible, we're going to focus on just 3 benchmarks today. The first is PRSA, RSA encryption algorithm. It's a compute-intensive program. The other 2 programs are versions of a sum-Euler symbolic computation. This is a memory-intensive program. It maps the Euler's totient function over an interval, a large list. And there are 2 versions. There's a data parallel version that allocates a huge list at the start of the execution and then consumes it. And then a divide and conquer version that repeatedly splits the list, creating sublists throughout the execution. And as you can imagine, these have rather different memory behaviors. So the first stage of our investigation was to use existing tools to profile what these programs were doing on Numa. And the first profiles I'm going to show you are Ghc heap profiles that plot residency against time. So execution time is on the x-axis, and residency measured in bytes is on the y-axis. The resident data is attributed to some function in the program in this grayscale, but that detail doesn't matter here. So what we see for this program is, well, it runs in, I don't know, about 550 seconds. It has, initially, it allocates a huge amount of memory. This is the data parallel version of the program that starts by allocating all these lists. And gradually, as those lists are consumed, residency falls. Now, these residencies aren't huge by modern standards, but compared with the other benchmarks, this has fairly high residency and a total allocation of 1800 megabyte seconds. So that's simply the product of the bytes, the resident bytes, and the number of seconds that they are resident. The sum Euler solves does the same computation, but has a very different heap profile. There's constant allocation of the sublists, which means that the residency is fairly steady throughout the execution of the program. It has lower maximum residency, 0.9 megabytes compared with 5 megabytes, and the total allocation measured in megabytes per second is rather lower. And finally, PRSA has a different profile again. It allocates continuously during its execution, gradually increasing the residency. Broadly speaking, this is fairly low, 1.7 megabytes compared with 5 megabytes for the data parallel sum Euler, and a fairly low total allocation, around 9 megabytes a second, compared with 1800 megabytes a second for the data parallel sum Euler. So these are programs. So this is not a data intensive program; it's compute intensive. So we choose these three benchmarks because they exhibit different patterns of Numa memory usage. These profiles are bog standard GHC tools. You set a run command line flag to generate them. Okay. So the next thing we did was to use the Numa Prof tool, which is available. It's an operating system level tool, and we set out to study the access from threads in one region to memory residing in a different region. And so what that gives you is an n by n matrix. In fact, there's an unpinned row here as well. So some threads are not pinned to any given Numa region. And the things to note here, well, blue means low levels of access, purple means higher levels of access, and red means is the highest level of access. So this is a heat map, and red is the hottest, blue is medium, and purple is medium and blue is cold. So the features of this heat map are a purple diagonal, meaning that each threads in each region do a significant amount of region local access. That's a good thing. Access to remote regions is mostly low, but there's this hot column where threads are accessing lots of threads are accessing region 3 from every other region. If we look at the other benchmarks, we see very similar pictures. So we again have the purple diagonal, local access. That's good. We have a hot column. Now this hot column, there's always a hot column. When you run the program, the hot column moves around. So these are the results I'm showing you for one specific execution. If you run it again, the hot column may be, the hot region may be a different region. Some analysis, we think the purple diagonal is probably because of the Ghc 8.2 local allocation policy. It's a little hard to understand the hot column at this point. Perhaps knowing how data is out, how the runtime system is allocating data within regions will help, and we'll return to that later in the talk. Analyzing the data we have for now, so looking at access vacancies, we can look at what percentage of accesses are local, what percentage are at distance 16, and what percentage are at distance 22. For some Euler, there's the 2 different versions, and for PRSA, there's just the one program. And we see that there is a significant amount of local access. This is around about 30% here for the data parallel programs. That is a lot more than you would expect if you had allocated data entirely randomly across 8 regions. You'd expect to have 12.5% local access. So the Ghc 8.2 adaptation is being effective. It's increasing the amount of local accesses. The increase is greater for data parallel programs because they're doing more allocation, so they can take greater benefit from the allocation optimization. We also propose that, well, we'd like to compare these programs. How much load are these 3 different programs placing on the memory system? And we propose the following metric for comparing that load on the memory system. It's Numa access rate, so it's the number of accesses per unit time, but weighted by the distance of that the access is made at. So on Togian, there are 3 different distances, 10, 16, and 22. So we compute the weighted access rate in the obvious way. We multiply the number of accesses by the distance, add them all together and divide by time. And we see that the data parallel sum Euler places higher load on the memory system than the divide and conquer, and this is because it initially creates the lists, and that forces threads to make remote accesses, so it places a load which is about twice as great than divide and conquer, which is creating local lists, and so doing more local accesses. Interestingly, PRSA, although it only runs for half a second, is placing a far higher load on the memory system by this metric. So about 3 times greater than, or 3 or more times greater than even the data parallel sum Euler. So that was the information we could gain with existing tools, existing memory management and profiling tools. But we thought that it would really help us to understand where GHC was allocating which region GHC was allocating memory into, because where you allocate the memory determines all future accesses currently. So we extended Numa Prof. We could have looked at this within GHC or within Numa Prof. We decided to do it in Numa Prof because it already has a malloc tracker called Molt. So you can look where those mallocs are targeted. And we recorded the allocations made by each thread into each region. The code is available on GitHub. So the profiles are, again, heat maps, and hugely unsurprisingly, there is this diagonal where all of the allocation, or the allocation from all the pinned threads is entirely local, and there's no allocation anywhere else. That's exactly what the GHC 8.2 optimization does. However, the unpinned main thread does a huge amount of allocation into one specific region, region 3. And if we look again at the other profiles, we see the same pattern. And specifically, the allocation into region 3 exactly corresponds to the hot region in the access profile. So the allocation profile explains the unpinned thread has done its allocation into region 3, and all of the other threads running in all the other regions need to access the data from the main thread, and hence create this hot region. The second thing we thought to do was to look at Ghc Garbage Collection to understand how that impacts on Numa. We are aware that various language implementations, in particular various JVMs, have used garbage collection as an opportunity to optimize Numa. So they detect opportunities to move objects during garbage collection closer to the threads that are using them, i.e. into the region where the threads using them are executing. So that's a big driver for understanding what the garbage collection is doing. So the first thing we did was to record how many garbage collections happen in each region, and of course how many of each type, generation 1 or generation 2 collection, are occurring. These counts supplement a whole bunch of Ghc garbage collection statistics that are already collected. So the number of bytes moved, GC runtimes, there's a whole bunch of stuff collected by the runtime system. So here's what the results look like. So for the 3 benchmarks, how many generation 1, generation 2 collections there are. And I've highlighted in yellow the hot region in each case. To be honest, these results don't tell us a huge amount about GHC usage of Numa. We see that there's, for example, a lot more generation 2 collections for some Euler. That's because sublists have been allocated early. They survive in generation 2 and force more collections than, for example, in the divide and conquer version of the program. There's a lot fewer garbage collections for the compute and not memory intensive PRSA program, but we don't really learn all that much about Numa from these statistics. The next thing we did was to look at the locality of the objects touched by the garbage collection threads. So how local or remote are they? There's three different kinds of objects being, three different things being profiled. There's generation 1 collections, there's generation 2 collections, and static objects. And this is similar logically to thread access locality. And in fact, we use the Numa Prof user interface to generate the same kind of heap maps, but these are heap maps of GC threads. What we see for generation 1 and generation 2 collections is good locality. So many of the objects being processed by the GC threads are local, and then small amounts of remote access. Generation 2 is similar, although there is a bit more remote access. But for the static objects, there's no locality. So these objects are evaluated by the first thread that touches them. The threads could be from any region, and so they reside in any region, and garbage collecting them then means traversing potentially many different regions. And we think this could be an opportunity to improve the garbage collection by moving these statically allocated objects to be closer to the threads that use them. Okay, so I'll briefly summarize what I've said. We've profiled Ghc Numa using both Ghc and Numa Prof, so using existing tools, looking at memory residency allocation. We show that there is good access locality, slightly better for data intensive programs than for compute intensive programs, but we saw a mysterious hot region, and we proposed an access rate that allows us to compare the loads that different programs are placing on the memory system. We extended Numa Prof using the MALT tool to look at allocation locality. Unsurprisingly, there's 100% allocation locality for sparked threads, but the main thread allocates a significant amount of memory into a single randomly selected region, and that region explains the hot region in the access profiles. We extended Ghc to look at GC counts per region and per generation per region. Honestly, didn't learn very much. Thread locality, looking at GC thread locality, shows good locality for generations 1 and 2, no locality for static objects, and possibly the opportunity to improve locality during GC. As I say, that's the kind of trick that other language implementations have used effectively. So what we've done is we've used the programs to understand some well-known Haskell benchmarks, but we haven't actually used them to optimize them to improve the performance, and that is definitely something that we should aim to do, use the information to improve the performance some programs. There are various ways we could improve the profiling. The profilers are already pretty slow, of the order of two orders of magnitude, and the Numa profiling adds to that, makes that even worse. So the profilers would be more usable if we optimize them somewhat. But the long-term goal is to use what we've learned about how GHC is managing Numa memory to do that better, and I'm quite ambitious. I think for Haskell it might be possible to get improvements of the order of 25% on a reasonably large Numa architecture. And that's it. Thank you for your attention.
Profiling is a bit of a black art, so I'm always happy to see work that tries to explain and develop new techniques. So we are technically at the end of the session, but since we have a break after this talk, I think we have time for questions anyway. So
I thought the schedule meant I could talk until 2 o'clock, trolls.
Sure. The question is whether people will stay around to listen to you. But I'll go through the questions in upvote order. So here is the first one. So the maximum residencies and the benchmarks likely fit in the level 3 cache of the course and the processors in question. What effect does this have on memory access latency analysis?
Yeah, you're right. These benchmarks are old and small, so quite possibly we should have used benchmarks with that used more memory. Yeah, we didn't.
So quick follow-up, does that mean we need better or newer parallel Haskell benchmarks?
I think it probably does. There are quite a lot of parallel Haskell benchmarks and lots of versions. I think it'd be fairly easy to increase the scale of those. Good question.
All right, we have another good question, because they're all good. Could the type system be leveraged to determine that a type/array is used only by the thread that allocates it, and to give hints to Ghc to keep the type Numa local?
Wow. Well, there are, of course, functional languages, non-strict functional languages like Clean, that have uniqueness types and are able to do exactly that kind of thing. So in a language like Clean that had uniqueness types, that kind of thing could be done. Haskell doesn't have uniqueness types. I would maybe defer that to people who know more about how to use the type system. So in theory, yes. In practice, I'm not sure.
Okay, then I have 2 small questions. So how does a profiler count memory accesses that hit the local cache?
I don't know. I don't know the answer to that. Hans Wolfgang is in the session, but so he might be able to answer that afterwards.
Yeah, and I guess that's Numa Prof that will have to be consulted to figure out what it's doing, right?
That's right. That's right. Yes.
Okay, so the last question is also from me. So does Haskell need its own metric for comparing Numa loads? And I don't know how people normally compare these things, but is your metric Haskell specific, or could it be used for any kind of Numa program?
I don't think it's Haskell specific. In fact, a lot of the metrics that are used for measuring Haskell are in terms of bytes. And that's rather strange because the runtime system is allocating objects, and objects are often a lot larger than bytes. So in some ways, we are measuring things at really quite a primitive level rather than thinking in terms of closures or other objects. The metrics I've reported, and in particular, the Numa access rate is measured in, I think it's bytes distance divided by time, but it's bytes. That's quite a long way of saying actually that the metric is low level and could, I think, be applied to other languages. I'm not sure whether people have tried to compare Numa loads before. If they have, I don't know if that work.
All right, let's see. We got one very last late question. Is the current Haskell allocator aware of Numa architecture when it allocates memory? Will this make a difference to allocating in the young generation?
Well, yes. So currently, the optimization, I should have said, is due to Simon Marlowe. He did it when he was at Facebook, and he optimized Ghc 8.2 for Numa because that gave performance benefits for the code he was running at Facebook. And the allocator allocates for Spark threads, all the allocation is done into the local region. So yes, well, it's Ghc Haskell allocation is Numa aware. It's done locally.
Great. Okay. Well, no more questions. Thanks for your presentation. I will now remove you from the stage.
Okay.
Yeah, final applause.
Your attention, guys.
Yeah. So now we have a rather